A wave is a traveling disturbance in a material. The material itself is not traveling, only the disturbance travels. If you imagine throwing a stone into a pond, the water next to the stone does not travel to where you are, only the ripple in the water travels. Waves can be broken down into a couple of types. The traveling wave or transverse wave occurs when the disturbance direction is perpendicular to the propagation direction. So here we have a picture of a person wiggling a string up and down and sending a pulse down the length of the string. The disturbance direction is vertical, but the wave is propagating in the horizontal direction. Another kind of wave is a longitudinal wave, where the disturbance direction is parallel to the propagation direction. So with the string moves up and down. That's the disturbance. Here, the disturbance is in the horizontal direction, which is the same direction as the propagation direction. Sound is an example of a longitudinal wave, and here we see a cartoon of what happens when sound waves propagate through air molecules. Each one of the air molecules is just moving back and forth. So if you see, there are a couple of red dots representing individual air molecules, and if you watch any of those red dots, you'll see that they just are wiggling back and forth. But the high density regions of air, those disturbances are propagating throughout the air column. Water waves are actually a mixture of traveling and longitudinal waves. If you look at any one water molecule, especially near the surface of the water, you'll see that it goes in a circle. And a water molecule deeper in the water travels in a smaller circle. Solitons are solitary waves, where there's only just one that travels along. These were first described by John Scott Russell, who noticed that when the doors on the lock in the canal that he was standing next to closed, he could see a single solitary pulse, a wave, travel down the canal. He was so interested that he actually jumped on a horse and chased the wave for many miles before it finally died away. Continuous waves, waves where there's not just a single pulse, but an ongoing set of disturbances, can be described as a traveling sine wave that moves along. So for a transverse wave, where the material is going perpendicular to the direction, you can see easily how if we make a sine wave that follows the shape of this traveling wave, that as the wave travels, this sine wave would scoot along to the right. A longitudinal wave can also be described with a sine, but instead of the sine wave describing the shape of the material, it instead describes the density. So high density regions correspond to a peak in the sine wave, low density regions correspond to a trough in the sine wave. And once again, as the high density and low density regions move along, so does the sine wave move along with time. So one can actually describe every single little bit of material that goes into making up a wave as a simple harmonic oscillator. So here we have a picture where there is a continuous wave being produced in a string, and if we take a look at any particular piece of that string, so any piece represented by one of those red dots, you see that it goes up and down, just like a mass on the end of a spring, just like a simple harmonic oscillator. You can also see that one wavelength is the distance between adjacent peaks or adjacent troughs, and the amount of time it takes one wavelength to pass any of the points in the string, the string will have undergone one complete up and down oscillation. So the wavelength, as we just mentioned, is the distance between two identical points on a wave, and we use the Greek letter lambda to represent that distance. The wave speed is the speed that a crest will travel along. So if you look at any one of these crests, it will move towards the right, and the speed with which that crest moves is the wave speed. So as we mentioned on the last slide, in one period, the amount of time it takes for any point on the wave to go down and back up again, in one period, the wave will have traveled one wavelength. So in one complete up and down period, the peak will have moved along down the wave by one wavelength. So that means the wave speed is going to be the distance that a crest travels divided by the amount of time. And in one period, the wave will travel one wavelength. We also remember that 1 over the period is equal to the frequency. So this equation describes the velocity of a wave in terms of its frequency and wavelength. And this is sometimes known as the wave equation. So next, let's use this equation to analyze a sound wave. So bats can detect small objects, insects, that are of a size of one wavelength. So if a bat emits a chirp at a frequency of 60 kilohertz and the speed of sound waves in air is 330 meters per second, what would be the smallest insect they could detect with that chirp? So let's first write down some of the numbers that the problem gives us. We're told that the frequency is 60 kilohertz of this sound that the bat is making. So that means the frequency is 60 kilohertz, so that's 60 times 10 to the third hertz. And we are told that the speed of sound is 330 meters per second. So that is the speed of our sound wave. So the wave equation states that the speed of the wave is equal to its frequency times its wavelength. And what we want to find is what the wavelength is, because that will tell us the size of insect that the bat can detect. So if I'm solving for the wavelength, I divide both sides by frequency. So the wavelength is the speed divided by the frequency. And the speed of these waves is 330 meters per second. And the frequency is 60 kilohertz, 60 times 10 to the third hertz. And the hertz is 1 over a second. And so then if I do this division, I get an answer of 5.5 times 10 to the minus third meters, or 5.5 millimeters. So 5.5 millimeters would be the smallest insect they could detect with this chirp. So next, let's consider this question. Some people in a stadium do the wave. What type of wave is this an example of?